Okay, tricky little question, this one. The jet's radar system sends out a pulse of microwaves, and at a time of 210 microseconds later, it detects an echo from the storm up ahead. So yeah, just a wee bit of background. Airplanes do have their own radar systems on board, so this one sends out radio waves that can be reflected by water and storm clouds. Travels back to it, the plane can detect it, and then can travel around either above, below, left, or right of that storm. It's one of the reasons flights are much smoother now than they were, say, 20, 30 years ago. Um, how far ahead of the jet is the storm? We need to find the distance, and the speed is the speed of the light, which is 3 by 10 to the 8 meters per second. What we said was microseconds. We have to convert this into seconds. We can divide by a million, or else we can just enter into our calculator by 10 to the minus 6 on your calculator, whatever you're most comfortable with. Works. There should be a little button on your calculator, maybe left of the equal sign, that is by 10 to the x. Just type that, put in minus 6, and it will give you those numbers. So let's do speed equals distance divided by time. 3 by 10 to the 8 equals the distance divided by 210 by 10 to the minus 6. 3 by 10 to the 8 multiplied by 210 by 10 to the minus 6 equals the distance, which will give us 630 by 10 to the 2, which is just 63000 meters as the distance. However, we're asked for it in kilometers, so we have to divide by 1000, which will give us 63 kilometers. But remember, this is an echo question, so that's the time to the storm and back again. That's therefore is the distance to the storm and back again. We're just looking at for the storm, so we have to remember at the end, divide by 2, and that will give us 31.5 kilometers. Next one says the jet itself, so we're not talking about the radar wave or anything like that. The radio wave we're talking about. The jet travels at a speed of 220 meters per second. We are distance to storm 31.5 kilometers. But we also have to remember there that we need to convert that back into meters to answer this question, because this is in meters per second. And we're just doing speed equals distance divided by time. Not dealing with echoes here, because we're just having a plane getting to that storm. So 220 equals 31500 divided by t, which will then multiply by t will give us a time of so we do 31500 divided by 220, and it gives us 143. Let's round it to there, seconds. But if we divide that by 60, we'd be able to divide it by 60 twice with a remainder. So if we subtract 120 seconds from that, it gives us that's 120 seconds and 23 seconds. But 120 seconds is just 2 minutes. So it is 2 minutes and 23 seconds. The frequency of the microwaves that reflect the storm is higher than the frequency of the microwaves in the original pulse. What does this signify about the storm up ahead? This is a little bit complicated, but if you imagine you have a race, you have lots of people who all run at the same speed conveniently, and you start them off, say each of them 1 second apart, and you let one person go, and then the next person go, and the next person go, all run at exactly the same speed, 1 second apart. They get to, say, a wall, and then they turn around and they come back. You would expect them when they come back to still be 1 second apart, 1 second apart, 1 second apart. However, if you have a race, say to a car, okay, and that car is moving, the first person will run to the car and back again. But if that car is moving towards the start line, the next person won't have to run as far. And therefore they will catch up a little bit with the person in front of them, and you'll find the people at the end will be more bunched up. And that's what's happening here. If we get a higher frequency, i.e. the wavelength's shorter, the waves are more bunched together. When the waves return from the storm, it means that the storm is moving towards us. towards the plane. This is particularly useful because we can see what direction it's moving in, but also it's particularly useful for if you're detecting other airplanes, particularly if you're talking about fighter jets and stuff like that. They can tell not only where the other fighter planes are, but also if they're moving towards them, if they're moving away, and a lot more information. Okay, last one. Satellite in orbit around Earth uses radar to map the Earth's surface. If a satellite sends out a pulse of microwaves and detects an echo from the Earth's surface after 1.2 milliseconds, that's not microseconds, how far above the Earth's surface is the satellite? So we actually use this for planet Earth, but also when we send little probes around other planets. This is our little satellite. It's sending a signal down to planet Earth and back up again. And if we time how long that takes, we can tell how far away the surface is. And then if there's a little mountain and the satellite flies over that, that time will be shorter, and therefore we know that the altitude of the surface is raised. So if we just extract the information, time 1.2 milliseconds, speed 3 by 10 to the 8 meters, we can actually just write that as 1.2 by 10 to the minus 3 for milliseconds, or we can divide by 1000 to convert milli into seconds, and we'd end up with 0.0012 seconds. Let's just stick with that. Trying to find the distance. Speed equals distance divided by time. 3 by 10 to the 8 equals distance divided by 0.0012. So therefore, if we multiply by that 0.0012, that will give us a distance of, just type that in my calculator, multiply by 360,000 meters, divide by 1000 gives us that is 360 kilometers. But we have to remember this time was the time down and up, so this is the distance down and up. We're just looking for the distance above the Earth's surface, so we have to divide by 2 and get 180 kilometers. Okay.